Ever wondered what's really going on inside the mind of a machine? Well, today we're going to pry open that black box of artificial intelligence. We're going to build an AI right here from the ground up, concept by concept, and really see how it goes from just following basic instructions to a system that can see, reason, and even learn.
I mean, think about it. We're surrounded by this stuff. It's in our phones, our cars, pretty much everywhere. But that familiarity kind of hides a huge mystery. When you ask your smart assistant a question or a character in a video game totally outsmarts you, what is actually happening under the hood? How does that machine decide what to do next? That's the big question we're going to tackle.
And the key to understanding pretty much all of modern AI comes down to this one single idea: the intelligent agent. You can think of it as the main character in our story today, because everything an AI does, whether it's playing a game of chess or driving a car, can be understood as an agent trying to hit a goal out there in the world.
So, what exactly is an agent? Well, at its most basic level, it's just something that can perceive its environment, through sensors, and then act on that environment using actuators. But hang on, that could describe a simple thermostat. The real question, the interesting one, is what makes an agent intelligent? Okay, this brings us to a really important idea. In AI, intelligence doesn't mean thinking like a human. It's all about acting rationally. A rational agent is simply one that, based on everything it's seen so far, picks the action that's most likely to help it win, to achieve its goal. Let's go back to that robot vacuum. Its sensors see dirt. Its goal, its performance measure, is to maximize cleanliness. So, the most rational action? You got it. Move towards the dirt and clean it up. It's all about making the best choice to get the highest score. All right, so our agent has a goal, but how does it figure out the steps to get there? If our little robot vacuum is in the living room and its goal is to clean the kitchen, it needs a plan, right? This is where the whole idea of search comes into play. The agent has to literally search through all the possible moves it could make to find a sequence that actually gets it to the goal.
But as you can imagine, not all search methods are created equal. Over here on the left, you've got uninformed search. This is the brute force way. It's like trying to find an address by just driving down every single street in a city. I mean, it'll work, eventually. But on the right, we've got informed search, which is way, way smarter. It uses a heuristic, which is just a fancy word for a rule of thumb or a smart shortcut. It's like using a map that points you in the general direction. It's the difference between wandering aimlessly and actually navigating.
So how does the heuristic actually work in practice? Well, the agent looks at its options, and it uses this thing called an evaluation function to basically guess which move will get it closer to its goal. For our robot vacuum, a really simple heuristic might be always move toward the biggest patch of dirt you can see. Now, it's not guaranteed to be the absolute perfect path every time, but it's a really smart guess that keeps it from wasting time, and it makes a gigantic search problem totally manageable.
These simple heuristics are great, but for really complex problems, our agent needs something more. It can't just react to what its sensors are telling it in the moment. It needs an internal understanding, a model, of how the world actually works. It needs to be able to reason about things it can't even see.
And get this! This quote from 1943, way before AI was even a real field, just nails the idea perfectly. The agent builds a small-scale model of its world right inside its memory. We call this knowledge representation. And with this mental map, it can basically simulate the future, it can plan ahead, and it can react to situations before they even happen. It's the huge difference between just blindly reacting and actually planning strategically.
And this, of course, leads us to the next big hurdle. Having a perfect internal model is awesome, but the real world is, well, it's messy, it's uncertain and totally unpredictable. What happens if the robot vacuum's wheels slip sometimes? Or what if its sensors are a little noisy and mistake a shadow for a patch of dirt? All of a sudden, the agent's perfect, logical model doesn't match up with reality.
To handle all this real-world messiness, our agent needs a brand new tool in its toolkit: probability. Instead of dealing in absolute certainties, things that are 100% true or false, it has to learn to reason about what is likely to be true. Now, this is a really fundamental shift in thinking. Logic is totally black and white. A statement is either true or it's false. That's it. But probability, it introduces all these wonderful shades of gray. It lets an agent hold a degree of belief. It might not be 100% sure there's dirt in the corner, but based on what it's seeing, it can be, say, 80% confident. This gives it a much more flexible and realistic way of seeing the world. And this is why probability is so absolutely essential. In the real world, your actions can have unpredictable results. A slippery floor might make the vacuum veer off course, and maybe more importantly, it helps the agent understand cause and effect. For instance, knowing that meningitis causes a stiff neck is a lot more useful than just assuming that a stiff neck means you have meningitis. See the difference? Probability gives our agent the math to weigh all this uncertain evidence, update its beliefs, and make the best possible call, even when it doesn't have all the facts.
So we have an agent that can perceive, it can plan, and it can even handle uncertainty. But there's one final, almost magical ingredient we need to add: the ability to learn. How does an agent get better over time all by itself, without some human programmer constantly tweaking its rules? This is the key to true autonomy.
The answer is this incredibly powerful idea called reinforcement learning. And at its core, it's beautifully simple. The agent just tries stuff, and the environment gives it feedback, either a reward or a penalty. You can think of it as trial and error, but a really, really smart kind of trial and error.
So let's watch this learning loop in action. It's pretty straightforward. First, the agent looks at where it is and decides to take an action based on its current strategy. Let's say our vacuum decides, okay, I'm going to move right.
Next up, the environment talks back. It provides feedback. If moving right led it to a nice patch of dirt, fantastic. It gets a positive reward, let's say +1 point. But if it bumps into a wall, well, that's a bad move. It gets a penalty, a -1 point.
In this final step, this is where the real learning happens. The agent uses that feedback to update its own strategy. It reinforces the connection that says, hey, when I was in that spot, doing that thing led to a good result. Now, imagine this tiny little cycle happening thousands or even millions of times. The agent slowly builds an incredibly complex strategy from maximizing its rewards. It literally learns the path to cleanliness all on its own. This is how it becomes autonomous.
So let's end with a really common objection, something you hear all the time. Surely computers can't be intelligent. They can only do what their programmers tell them to do. But after seeing how an agent can be given a goal and the ability to learn its own strategy from scratch, does that statement still really hold up? By learning from simple rewards and penalties, an agent's behavior can grow to be way more complex than its initial programming. It really makes you ask the question, what does it truly mean to tell a machine what to do? Definitely something to think about.